This is Group 9's final project for feedback controls, the magnetic levitator.
The members of this group are Kallen Campbell, Doug Deboer, Josh Robinson, and Nick Walker. We are all 4 electrical engineers.
The purpose of this project is to have a relatively lightweight metallic object levitate at a small distance below a magnetic solenoid. The levitated object is attracted by an electromagnetic force that is placed above the sphere and obtains equilibrium when the electromagnet matches the force of gravity.
The materials used in this project consist of a levitating object such as a steel ball bearing, which is 0.68-inch diameter with a weight of 0.7 ounces. We also used a steel plate, which was 1.9 centimeters by 1.9 centimeters and weighs 0.1 ounces. The magnet we used was a 12-volt electromagnet with a peak force of 250 newtons and 185 newton holding force. After many unsuccessful attempts with a 12-volt laptop power supply, we switched to a variable power supply where we could manipulate the voltage so we could precisely control the voltage to the magnetic solenoid. For support, we 3D printed a rectangular frame that has a hole in the top to conceal the magnetic solenoid. For the sensor, we selected a KY024 linear Hall effect sensor, which has an operating voltage of 2.7 to 6.5 volts. We then connected this to the Arduino to help process the data received by the sensor. As you can see on the left, we have a picture of our 3D frame from a side and top point of view. Also, on the right is our final prototype for the project.
For this project, we used a TIP 102 MOSFET transistor. From the data sheet, we have the collector, emitter, and base voltage rated at 100 volts DC, the collector base voltage at 5 volts, the collector current at 8 continuous amps, the collector current peak at 15 amps, and the base current rated at 1 amp. As for the driver, we used an Arduino transistor and a diode, and the diode was used to exfoliate any excess current from the solenoid.
The control principles for our project is to use a magnet to levitate an object. To turn on and off the magnet very quickly, we use an Arduino code and a linear Hall effect sensor. The linear Hall effect sensor was used as a feedback loop to turn on and off the magnet, which allowed us to levitate our object.
So this is our block diagram for our control loop for our magnetic levitator. We have 2 inputs, one f of s, which represents the disturbance due to the force of gravity. It has its own separate transfer function block with the coefficients k of m from the magnet and the equilibrium operating points of the distance and current. We also have a feedback loop from the function of distance y of s with k of s that represents our linear Hall effect sensor. As you move on down the line, you reach h of s, which represents our controller. We tested many theories here, but ended up resulting in using a PD controller for h of s, which is kp plus kd times s. As you move past the controller and reach the negative summation with f of s, the disturbance, you reach the total closed loop transfer function. Most notably, you have the closed loop denominator with the equilibrium distance y naught squared times mass times s squared minus km, which is, as previously mentioned, the magnetic solenoid coefficient, times the current at equilibrium squared. And finally, this wraps up the most simplified block diagram for our control loop.
The diagram on the left shows our beginning prototype, showing the magnet lying above the sphere with a small screw on top. We quickly changed this design by removing the screw and sphere and using a steel ball bearing and metal plate. Even with the change of materials, the principle for levitating the object remained the same. In the diagram shown, we were solving for the balance of forces required to levitate the object, with F of m equaling the force due to the magnet, F of g being the gravitational force, and F of I being the inertia force.
As for the balance of forces, since the distance is inversely related, we have to linearize the equation. And to do so, you must find the variation of I by finding the slope and finding the partial derivative of the magnetic force with respect to the current evaluated at an operating condition.
After solving the loop equation, we come to the highlighted equation below in the bottom picture as a function of y of s. We have 2 inputs, I of t, which represents the current as a function of time, and mg minus f naught, which represents the force due to gravity. After evaluating the denominator to find the pole locations, you can see that both poles are real values. one on the positive real axis and one on the negative real axis.
Now with the code, we initialize variables and pins used to take in the analog sensor data and output the trigger pulse. The SP value is the point that is changed during testing to find the right distance from the sensor where the object will levitate. In setup, we set the sensor as an input and trigger as an output. In the main loop, it reads in the sensor value and then compares the SP and sensor values to turn on the solenoid if the object is too far below the levitation point, and turns it off if it goes above that point. If the object is not in sensor range, the solenoid is turned off to put it in a sort of sleep mode. No delay is used in the loop, so the code reads the sensor and adjusts accordingly as fast as possible.
The trials and demonstrations you are about to watch will show us trying to overcome the obstacles, such as combination of Kp and Kd gain values, the weight of the object being levitated, and the distance between the sensor, magnet, and object. We chose an object with a flat surface to reduce the spinning, so rather than using a screw, we used a steel metal plate. Also, you will see the unstable behavior that occurs, such as oscillations throughout the demonstration.
It did just there for a second. Oh, this is making me happy.
I'm gonna keep going down. The main issue that we had with the hardware was finding good placement for the linear Hall sensor. We started testing with the sensor underneath the levitating object, but after several failed attempts, we attached the sensor directly underneath the magnet. We then tested the magnet's effect on the sensor reading, and it found it to be negligible. The other issue we had was finding the correct orientation of the permanent magnet and Hall sensor to get the Hall sensor to read correctly and accurately for our purpose. This was simply solved by trial and error.